Alright, so good day everyone. In my last lecture, I started with systems under thermodynamics and I explained the terms systems, surrounding, boundary, and some types of systems under thermodynamics. I explained open systems, I explained closed systems, and isolated systems. In this lecture, I'm going to be explaining isochoric and isobaric systems. So what do we call an isochoric system? Isochoric systems. Sometimes we call them isovolumetric, and sometimes we call them isomeric. Now, the first thing I want you to take note here is that when you hear the word iso, it simply means same. The word iso means same. So when you say isovolumetric, it simply means same volume. It simply means the volume is constant. So when the volume in a system is not changing, the system is called an isochoric or isovolumetric. Now, let's say I have a container, a beaker now to be specific, and I have the wire guys, I have a tripod stand, I have the Bunsen burner which supplies the heat, and then let's say I have piston which supplies the pressure, and let's say I have gases in this container. Now this supplies heat, which is temperature. This supplies pressure. It simply means for the volume of this container that involves the gases to be constant, it simply means the pressure and the temperature must be applied directly. Okay, and that is why in an isochoric system, the law that governs isochoric system is called the Geluzas law, which is basically telling us that the pressure is directly proportional to temperature, but the volume is constant. So I can say pressure is equal to kT, then K is equal to P over T. So I can generate a sequence here and say P1 over T1 is equal to P2 over T2 in that respect. Okay, so this is the law that governs an isochoric system. And I want you to take note that the work done in an isochoric system is always equals to zero. Now, how do we go about the work done? As we all know in physics, that work done is always equals to force times the distance. Okay, and also if recall the pressure is equal to force over area, and then when I cross multiply, I'm going to have force to be equals to pressure times area. Shows that anywhere I see force, I'm going to substitute pressure times area. So I can come back here and say work done is equal to pressure times area times the distance. Now the distance could be the height of the container. So area times distance, which we are taking as the height, is equal to volume. So I can say work done is equal to pressure times the volume. So the work done is always equals to pressure times the volume. So before we could have work done, that is change in work done, there must be change in volume. Change in volume. So anytime the change in volume is equal to zero, it simply means there is no work done. And that is why the work done in an isochoric system, the work done in an isochoric system is always equal to zero, because the change in volume is equal to zero. Okay, and the graphical representation of isochoric looks this way. Okay, so here we are plotting pressure against volume. But remember that the volume is constant, but the pressure is changing. So that is why the graphical representation is always in this manner. So this is the graphical representation of isochoric system. All right. Now the next system that we are going to discuss is isobaric. We are going to discuss isobaric. Isobaric